Now we're recording. All right, so for you guys at home, have this rotational inertia lab printed and ready to go. This is going to be your main focus today. But I got a few warm-up activities to get you guys thinking about physics. So, yeah, you guys see this question over here? Which way will the spool rotate? Okay. Let me show you literally what's going on. Right, so I got this spool. Okay. Ooh, you guys see how it has like an inside radius and an outside radius? Okay, two circles. Okay. Oh, and you see how I have the string wound around the inside? Okay. Something like that, like a string wound around. Okay. So this first picture, what I'm doing is I'm just pulling this string straight up like this. It's pulling straight up. Okay. Which way is that going to cause it to rotate versus what if I change the orientation of the string? Okay. So think about those questions while I'm grabbing my attendance, and then we'll come back to that. Okay. All right, looks like we got everybody here. Everybody present, ready for the lab. All right, so this is what you guys came up with. I want to see a hand vote on each of these, and then we'll see how well you guys do. Right. So for this first one, I mean, you got two options, right? Either it can rotate clockwise off to the right or counterclockwise off to the left. Right? So show of hands, how many guys think it's going? Oh, hold on a minute. Time out real fast. We're missing Morgan. All right, yeah. Hold on. Let me update my attendance real fast here. Okay. Okay. Right, so back to here. Right, so how many guys think this is going to rotate off to the right clockwise to the right? Right, so I see a bunch of hands. Right. Does anybody say counterclockwise to the left? Nobody says that? Right. Let's try this out. Right. So prop this down here. Let's see. I think it was pretty good on camera too. Right. It picks up. Yep, there we go. Clockwise off to the right. All right, so maybe not a big surprise. Right. What about this second guy right here? Right. What do you guys think for this one? Same thing. Show hands. How many guys say clockwise off to the right? Right. Ooh, that's that about everybody. Does anybody say counterclockwise to the left? Nobody says that. Yeah, let's try this out. Right, so pull this to the right. Oh yeah, it sure does go clockwise to the right. Okay, so no surprise, two in a row. Right. All right. What about this last guy? So pull it like that. Here's that guy going to rotate. Show hands. How many guys say also clockwise to the right, just like the first two? Clockwise to the right. Does anybody say that? Nobody says clockwise to the right? Who says counterclockwise to the left? Oh, there's a bunch of hands there. All right. Oh, let's try this out. All right, so let's take this, flip it upside down. All right, so I got the string now on the bottom, right? String's on the bottom now, right? All right. So most of you guys are saying counterclockwise to the left. Ooh, it's still clockwise to the right. Huh, it still pulls off clockwise to the right. All three of these rotate the same way. They're all clockwise to the right. Huh, right? What's going on there? Well, let's take this picture and blow it up a bit. Because got the outside radius, the inside radius, strings around. Right? Now, notice with all three of these pictures, I did draw the floor. See this hatched floor right here? Okay? Because that's the point that it's actually pivoting about, isn't it? Okay? Now, what you were probably thinking, and how you would have gotten the third one backwards from how it actually went, was you're probably thinking, well, maybe it's like rotating about this middle axis point. Okay? And so you were thinking about torque, right, R cross F, but you would have had the R value in the wrong spot. So if you do R being from here to here, cross with this F, the string tension could represent the force, right? If you did this R cross F, then that would be R cross F. That would be like a counterclockwise or positive torque, right? Which would have been true for the first two. Sorry. That's never mind. We go back. Right. But that's not actually what happened, right? So maybe there's a different pivot point that matters. And wouldn't it be this point where it's touching the surface? Right? Because this is actually a point of friction, isn't it? Right? So I've actually got an R value that goes from here to here. So this R cross F, yeah. So that's actually a negative torque, a clockwise torque. Right? And that's true for these top two also. These were also clockwise. So for this top one, maybe you're thinking R cross F, but really it's the R values from here to here, right? But same result, right? And then for this one, you were thinking probably R cross F, right? But it's really the R values from here to here. This one actually gets a lot more torque, doesn't it? Because it's a huge R value, right? And so we draw this a lot bigger. Here's the floor. Okay. Right, so remember, the point that it's rotating about is actually not the middle of the circle. It's actually this point right here. Right? So I'll specifically draw this this third one, right, where I'm pulling the string straight this way. Hey. Oh, all right. This is what pressure me. All right. Thank you.
Enjoy. Very good.
All right. Yeah. Thanks much. All right. So wouldn't this right here be my R value, and this would be my so I'm getting some R cross F. Yeah. So it still rolls off to the right. Right. Well, if that's true, yeah. Let me draw some other force vectors in here. Okay? Guys, which direction is friction acting right at this point? To the left, right? Isn't that, there's like a friction force, right? And then, so I've got tension force to the right, maybe F sub T, force due to tension, right? Force friction, right? Ah, look at that. That's what allows this to rotate like this, right? There's your torque, right? Well, if that's true, then, let's see, what if I change the orientation of the string? See, if I pull straight up, it would roll the way you would think it would. It's intuitive, right? If I have a force of tension this way, right? Then here's my radial door, R, right? So I've got this R across this F. That would make it rotate counterclockwise, right?
Interruption. Grade 9, last reading with the letters E through G should go to the auditorium for registration at this time. Grade 9, last name E through G. Thank you.
I don't think I have any ninth graders in here, right? Okay, so maybe I should have switched colors with that. Right? Maybe I should have go with like pink, right? So this pink R value and this tension match together, right? So then this R across this F, that would send it counterclockwise, right? The one you just saw that was maybe counterintuitive was if I pull down here, it went up clockwise. Well, hold on a minute. If I orient the string this way, it goes clockwise, and I orient the string this way, it goes counterclockwise. Do you think there's some orientation of the string in the middle where it all cancels out, that there's zero torque? Huh, how could I get that? Let's go with green for this one. Right. Now, if there's zero torque, shouldn't I be like pushing or pulling like straight on the door hinges? In fact, you know what, maybe if I line this up so that it lines up with this pivot point down here, this is the actual pivot point, right? Maybe something like this. If I have a tension force this way, or it's like lined up exactly with that, that should be zero torque. And if that were true, then would this thing not rotate at all? Right? Well, maybe it would slide because there is a rightward component. Maybe it would slide off to the right, but it shouldn't actually rotate. Do you think I could pull on the string on this somehow and get zero rotation? Is that possible? Let's try that out. I wonder if I can actually do that. Maybe I know because I've been teaching this class a long time. But probably right about there-ish. Hey, look at that. I'm pulling and it's sliding, but it's not actually rotating. Yeah, look at that. Sliding without rotation. Ooh. Got a spooky spool. Maybe yeah, for Halloween day. Throw a sticky note on here, make it super obvious in case it wasn't. At least for the camera, for you guys online. Yeah, look at that. Just driving right across. All right. Now there's something else that I actually want to talk about this because this reminded me of something, which is different points on the circle will rotate, will have different types of motion. I mean, this could be a car tire, couldn't it? Right. Let's think about this being a car tire. and what different points on this what kind of motion it would actually go through. Right? Let me start with one that's pretty straightforward. This point right in the middle. Right? If you just have your eye trained exactly on this point, and this car is rolling down the road, right? Then what does this point itself do? Moves how? Yeah, just like a straight line, right? Doesn't it just move in a straight line? Right? Just stays, one car radius, or one tire radius above the ground. Right? Let's think about something a little trickier though. What about a point on the edge, like this point here, or this point, or this point? Right? Any point on the circumference of the circle. Right? What's that going to do? Huh? It's going to look something weird, isn't it? Right? Because you can imagine this car rolling. Right? Now let's take a point on the periphery. See here, it's moving forward. Right? Now, when it breaks past this point, no, the car is still moving forward, right? And this actually, all these points are still always moving forward, but relative to the car down here isn't actually moving backward relative to the car, but it's still moving forward relative to the road. Right? And the same thing over here, it's moving backward relative to the car, but forward relative to the road. Right? But then the entire top half, it's moving the same direction as the car, but probably faster than the car itself, isn't it? If the car's going 60 miles an hour, I bet it when it's here, it's going probably twice that speed, I think. I think that would be true, right? Right?
Is that tangential velocity or angular?
Yeah, tangential velocity, right? Because the entire disk has the same angular velocity, right? The same radians per second everywhere. Right? But yeah, if you pointed like a radar gun at different points, then you should get different speeds, right? I'm pretty sure that's right. I think the top point is moving like twice the speed of the car. Right? The bottom point has an instantaneous speed of what? Yeah, 0, but just for that one instant, right? And then of course the middle is moving the same speed as the car. Right? So you can make an interesting graph of this. Now, here's where I'm going to flip over to present screen to share. Okay. So I went on an internet search this morning, and let's see, and look for that one. Okay, here's a good place to start. Okay. So it creates a shape called a cycloid. This is extra stuff. I mean, this is obviously not going to be AP exam, but yeah, it's fun to learn. So yeah, you guys see that red curve? Right? That's called a cycloid, and that's exactly what any point on the perimeter of your car tire is going to be. Right?
Very satisfying.
Yeah, it sure is. Yeah, I like that animation. Yeah. Guys, what is the height of the cycloid relative to the circle? Yeah, the diameter, right? That's the diameter of the circle. Right? What is the width from this point to this point? It is the circumference of the circle, wouldn't it be, right? Yeah, so it has a height of diameter and a width of the circumference. Huh. Right. You know what you can do is you can pick different points on the tire. So, like for example, the point right in the middle is just going to be a straight line, right? But I found this website. Let me zoom in here. Yeah, this like suddenly blows up. So boom, it's like one mouse scroll. It's unexpected. So here's your normal cycloid. Looks like that. You guys just saw that. But what if you pick a point like here? Ooh, kind of like a more straightened out cycloid. This point's a little bit curvier, right? Rather than a sharp point. Right? You can also pick a point that extends beyond, right? Like that Will's just showing you guys. Like, what if I rotated about this yellow tape? Let me show you guys online, right? What if it was like on a track like this, right? You guys could imagine that. It's like on a track like this, and I was looking at a point like beyond the circle that was rated. That's this last picture, right? You guys said, hey, look at that. It looks like a loop-de-loop shape. That's pretty cool. Okay. Now, I was reading on the site some interesting things about this. Right? One thing that you can do with the shape is, now maybe I need to double check this fact, but down here it says, it makes the shape called a verticichrome. Yeah, I really should double check this after school, and I'll tell you guys why too. But what a verticichrome is good for is, this is how you can go from this point A up here to the bottom the fastest. Like, let's say you're rolling marbles down there. Like, how can you get a marble back from here to the fastest? Right? Well, you might start by thinking, well, what if I just had a straight line distance? That would be the, like as the crow flies, that would be the shortest distance, right? But see, if you have a dip in the beginning, you actually get an advantage because that vertical height drop gets it moving faster in the beginning. So that will actually beat the straight line. Right? But you don't want to curve it, have it too vertical. Like, what if you had like a pretty close to an L shape, right? Because now there's a longer distance that has to go. So there's like a trade-off, right? And the verticichrome how do you pronounce that? Batista Chrome, right? Is the it would be the fastest way to get it down to the bottom. And what else the shape is pretty cool for? You guys see this animation down here? Is you can actually drop the marble from any height, and it will take the exact same amount of time to reach the bottom. So it doesn't matter if you drop it from here or if you drop it from like from down here, right? You guys see it takes the exact same time for all those to reach the bottom. Right? There's actually a Vsauce video on this too, which is pretty cool. Right? But here's why I say you need to actually double check this and fact check myself. It's because I was reading this text, and it actually does have an incorrect fact here if you stumble across the same website. Let's see, where is it? Let's do Control F on this. Yeah, down here it says that it would create the strongest arch. That's actually not true. Do you guys know what shape would actually create the strongest arch? Oh, I think it's this tab here. Yeah, it's something called a catenary. Right? And it looks kind of like a parabola, but it technically is not a parabola, even though it's pretty close to one. Right? How you can get a catenary is if you just like hang a string or a chain like from 2 points. See how this guy's like hanging a chain like this? Right? That will naturally form a catenary. So it's like a shape that nature wants to produce. So if you take that and you turn it upside down, that will create an arch, and that's actually the strongest arch you can possibly have. Right? I was surprised to see this picture, by the way, on my internet search this morning, because it says this is Robert Hooke. There's actually no known picture of Robert Hooke in existence, so we don't actually know what this guy looks like. That's who Hooke's Law is named after, right? With the springs, you remember that? But supposedly, what I remember reading a long time ago is that there actually was one portrait of this guy, but Isaac Newton destroyed it himself, at least according to legend. So anyway, there was a kind of a petty rivalry between those two guys. So yeah, and so that was a fun side quest there. But let's get on to our main thing today, which is actually this lab. So stop sharing that. Right, so get this back. Right, so we've got this rotational inertia lab. Actually, before I go through this table, I do want to show you the setup for this. So we need to measure or somehow find out what the rotational inertia of something's going to be. Okay? And we're specifically going to be looking at this shape, this T shape. Disconnect this from last class. Okay. So, yes, see how this is, I've got this spinning, right? It's very low friction. Right? There's a little bit of friction, but not much, right? So it takes some effort to get it going when that mature, right? But once it's going, then it also takes a while for it to stop, right? It stops because there is friction, but it wants to keep going to get ahead because it has inertia, right? Rotational inertia, right? Now, how do you think we could determine what the rotational inertia of this is? What's one way you guys can think? Like how much rotational inertia does this have? This T thing moving around. Oh, let me do this too for the camera. I'm gonna slide this back a bit because you see more on the frame. So this right here is spinning. So how can we figure that out? What's the rotational inertia?
mr squared.
Okay, yeah, maybe something about mr squared, right? So we're going to do this 2 different ways. The first way is not the proper lab way, but we'll do a comparison at the end. Okay, so yeah, I like that idea. Saying like, well, I remember for a single point it's mr squared, and doesn't this look like maybe like a thin rod rotating about the center? Yeah, Jerry.
Oh, yeah, I was gonna say, I think it's 112.
Yeah. So there's a table in your book, and I'm going to refer to it here in a moment. Right? That said, for a rod rotating about its center, it's like 1/12 mr squared, or for about its end, it's like 1/3 ml squared. Right? So let's try it that way. Right? Now, maybe that could be like a lower boundary condition for this entire T shape, because do you think this rod going down the middle also has a little bit of rotational inertia? Right? Maybe a little bit, but not very much compared to these arms. Right? These arms are supplying most of it. But maybe a little bit here. So let's try that first. Let's do the textbook method for like something to do with ml squared, some fraction of that. looking at these arms and figure it out that way. So let me grab the mass and length of each one of these, and then figure this out from there. So I can just grab one of the arms. I'm going to grab the mass. So I just reset this to 0. Pretend I didn't know what this was going to be already. This is balanced out. And it's pretty well balanced. Okay. Let's grab the mass of this guy. So 140, about 142 grams. So this guy has a mass of 142 grams. There's, see how long this would be from the center, right? So one of these arms is, let's see, 63 centimeters long, right? So, did you guys jot down those numbers? 63 centimeters long? Okay. Because I'm going to switch the camera and we're going to do a calculation before we get to the lab proper. Okay. So put this table and graph to the side for a moment. I'll come back to that. Okay. Yeah, let's do this textbook method that Kevin and Jared are mentioning. Right? And I wanted to start this way anyway, so glad you guys set us down this track. Okay. But yeah, remember this table from the book. Okay. So it looks like maybe one of these, right? Either rotating about center, rotating about the. Let's try it both ways. If you know only one of these, and you guys remember I was teaching you guys something called the parallel axis theorem, right? If you only know one of these, you can actually determine the other going through the parallel axis theorem because one is just the other just shifted axis, right? Okay. Right, so let's try it first for just a single arm, which would be more like this one right here, 1/3 ml squared, and then I'll just double that to account for both arms. Okay, and then we'll go back and we'll try it this way and see if it matches up. Right, so I for one arm should be what, 1/3 ml squared, 1/3 ml squared. Right, remember that's rotating about its end, so that's with the axis right here, and it's rotating about like that. So that's 1/3. The mass was 142 grams, right? So it's 0.142 kilograms. The length was, what was the length? 63, that was it? So 0.63 meters, and I have to square that value, right? Okay. So let's see what I get from that. So 1/3 times 0.142 times 0.63 squared. Okay. That's giving me 0.0188 thereabouts kilogram meter squared. Okay. Now that's for a single arm. So wouldn't I, for two arms, be just twice that value, 2 times that? Right? Which is, see, times 2. I'm looking at 0.0376 kilogram meter squared. Okay. No, of course, that's not including the axis down the middle, which would probably add a little bit to that, right? Something like that. Okay. Let's try it the other way. Right? So what if we considered the entire top beam and it's rotating about its center? Right? So it should be this exact same thing, shouldn't it? Right? If this is all self-consistent. Okay? So I, 2 arms could be, now this would be just my diagram set up. Okay? It's rotating about this axis now. Do something like this. Okay? It says 1/12 ml squared. 1/12 ml squared. Of course, it's twice the length that it was before. So the 1/12, it's also twice the mass, isn't it? Okay, so 0.284 kilograms, double mass, right? Double the length, so that's what, 1.26, I think, meters. Square that. Okay. So let's see if that's the same thing. So 1/12 times 0.284 times 1.26 squared. Okay. That's coming up. Oh, yep, it's the exact same thing. 0.0376 kilogram meter squared. There you go. So this should be pretty close to what the answer is. No, this is just a textbook value, right? All we did was follow these formulas. But the lab that we do, we're actually going to take measurements and do experiment and see how well it lines up to this. But ideally, it should land pretty close to this, shouldn't it? Right? So let's take a look at this lab page. Right? How are we going to get this experimentally? We're going to approach this from a different point of view. But I'm going to hold on to this paper because we're going to make a comparison at the end and see how close it was. Which, by the way, last class, it was actually surprisingly not close in the wrong direction. So it's like, but we'll get it when we get there. Right. So I'm going to go over this lab backwards. I think it's a really good way to explain this. Right, so let's start with this graph. Right. So it says tau versus alpha. Whoa, tau versus alpha. And somehow I'm supposed to get I from that, rotational inertia. Who can tell me when this graph comes together, what property of this graph will tell you rotational inertia? Yeah, the slope. Yeah, because you guys remember, this formula? Tau is equal to I times alpha. You guys remember that? Now, tau torque is also equal to R cross F, but this is the other formula for it, right? Sometimes you can set this equal to R cross F and solve things out. Right? And this is analogous to F equals MA. Right? Remember, you guys learned a bunch of linear stuff for the first few weeks of this class, and then in the last couple of weeks, we've been doing rotational stuff, and there's a bunch of rotational equivalent formulas, including this one. Right? Yeah, so this looks a lot like y equals mx, doesn't it? Right? Yeah, so you guys are exactly right. Something to do with the slope of this graph will answer this question. Okay? So how are we going to get coordinates for this graph? Well, we're going to need some tau values and some alpha values, right? Torque and rotational acceleration. Okay? So let's start with one. Maybe I'll start talking about alpha. Right? How now alpha is something to do with how fast it's speeding up spinning. Right? Actually, do this. Let me turn my camera so you guys can see the mechanics of how this is going to work out. Okay. I meant to do this is do at least one trial run. Okay. So see what I've got is I've got a string wound around this post, and I've got this through one of these pulleys. I'm going to take a weight, put it right here on the string. Oops. Here. Wind this back up. All right. And start to fall apart from my class. Right? And then I'm just going to let this weight fall. And as it does, it's going to spin this. You see it? And this weight is going to fall faster and faster, which is going to make the spin faster and faster. Right? You guys see all that coming together? Right. So that's the basic setup. Right? While I got this turned and we're just getting our feet wet on this, right? What would happen if I took these arms off? What do you think? You think it would? Yeah, you think it would fall down like crazy fast? Because these arms are adding a bunch of rotational inertia. In fact, it's most of the rotational inertia come from the arms, right? So what if pop, let's take these guys off. Right? I wonder what's going to happen now. Ooh. Oh, well, that's a lot of winding up I got to do. Right, well, right. That was to be expected. All right. Okay, so now you guys have seen the mechanics of how this works. All right, let's take a look back at that table and see if we can figure out how am I going to get tau and alpha from that, right? Torque and angular acceleration. Well, angular acceleration, alpha. You guys remember that is, what's the formula for angular acceleration? You guys remember it's linear acceleration divided by radial size? You guys remember that? Right. Okay, and see if I knew the linear acceleration of that falling mass, and I know the radial size of that post that it's wound around, that could get it for me, couldn't it? Because isn't that post, here's what you guys just saw. Here's that central post, that vertical post. There's a string wound around it, right? And, okay, we got a pulley system here, which has very little mass. This weight's hanging from it, some kind of mg going on. Right? Isn't that the setup. All right, so, do you think maybe there's a tension pulling right here at some radial arm distance? I got an R, I've got an F force, right? Hey, that's R cross F, isn't it? Here's the axis that's rotating about. Right? I got some R cross F. I'm talking about tau. Oops. Well, it's going to be applicable anyway. Right? But getting back to alpha versus A, right? Wouldn't A be the acceleration of this falling straight down? Right? And then here's the radius. So, it's literally tied to the post. Right? So all I have to do is divide by this radial value to get how fast this is speeding up spinning. Isn't that true? Right? Right? So that's how I'm going to get alpha. But hold on a minute. How do I get A? Because that's another thing. I could very quickly measure R. But what is A? Acceleration. Huh. Does that have something to do with how far it's falling and how much time? If it starts to rest, do you guys remember a formula that goes, how far it falls is 1/2 AT squared? You guys remember that? Okay. So, I bet I could rearrange this and solve for T. 2x on T squared. Okay. We did a very similar thing recently on the Atwood lab. You guys remember doing that? Okay. So, I'll get started. Oh, whoops. Yeah, sorry. Yeah, thanks. Good catch. Okay. Yeah. All right. So you guys got that? Okay. All right. Okay. So remember, explain this whole thing backwards. We know. Here, remind you guys what's going on. Right? If we have some kind of tau versus alpha graph, the slope is going to be the answer that we're looking for, rotational acceleration. But then how do we get these parts? Right. Well, alpha we're going to get from A over R. R is very easy to measure just with a ruler. But A we're going to have to use a meter stick and a stopwatch. Okay. Let's figure out the other way. Tau. Right. So torque, wouldn't that be this force crossed with this radial arm? Right. So let's do that. Throw this down here. Torque is equal to R cross F, and they are at right angles at all times, so that makes it easy. Right. Again, I could very easily measure that. Right. The force. Do you think the force is probably pretty close to what this weight is? It's probably pretty close, but is it exactly the same? It's not. Is it a little bit more, or a little bit less than the weight? You're right. It is a little bit less because this whole thing's accelerating down, isn't it? You know what this sounds a lot like? Tension in an elevator cable. That's what this is. Okay. Now, for AP, you'd have to derive that from scratch using free body diagrams, but you guys have seen that so much in here. You guys know that that is equal to mg minus a, right? For accelerating down. Or I should have asked you guys. This should have been g plus or minus a, but you guys would have said minus, right? Because it's got a little more slack because it's accelerating down. Okay, so now you guys seen like backwards in logic how we're going to put this all together. Okay. So let's take a look at this table now. Okay. So going from left to right, we're going to need the radial size of that post. Yeah, maybe about a centimeter, but I'll get a measurement on that. Okay. This mass refers to the falling mass. Maybe I should have specified that, but it's going to be whatever mass we're hanging, right? And that'll change throughout the experiment. We're going to have to measure what's the falling distance, what's the falling time. Ooh, somebody's going to need a stopwatch. Who wants a? Oh, Jared, you want a stopwatch? Yeah. Okay. Yeah. You got a stopwatch?
Yeah.
All right. Okay. Now, once we got those measurements, then we'll do this calculation for acceleration, right? 2x on t squared, just like I showed you. Yeah, we'll be able to get everything from there, right? The tension, mg minus a, all that. Okay. Right. So first thing, what's the radius of that central pipe, right? So I've got an equivalent piece. This is an equivalent piece right here, right? This is what the top of it looks like, right? So what is the radius of this thing? Let's see, and I want this in like centimeters or meter. Trying to see where it's both on the camera and on the screen. Okay. I'm going to use this off screen a little bit. Or actually, what? Maybe I can fit it in like this. That's great. The diameter is 2.2 centimeters. Okay. Now, if the diameter is 2.2 centimeters, then what's the radius? Yeah, 1.1 centimeters. But in terms of meters, wouldn't that be 0.011 meters? Okay, and that's going to be the same all the way down. So that's not changing. Right? We've got the same post over and over. Now the masses we're going to use. I'll also go ahead and pre-assign those because I did this last class, and so I found some pretty good masses. Okay. We're going to use, we're going to start with the 200 gram guy. So that'd be 0.20 kilograms. Okay. And then we'll add on 100 grams at a time. So let's go 0.30, 0.40, 0.50. And then at the very end, for fun, we'll do a 1 kilogram. Okay. Guys good there? All right, then falling distance. Now this will also be a value that'll be pretty much the same over and over. Yeah, we go ahead and turn the camera to the lab mode here and grab that, and then we'll start making our measurements here pretty soon. Okay, so what's the vertical drop here? Let's start 0 at the ground. Okay. Well, up to let's see. This, yeah, so this is 200 grams, and throw 200 grams right here. Right, wind this up. Right. And then, okay, so Jared, when you time this, time it from when it starts falling to where the bottom touches the floor. Right. So right now, the bottom of this weight is reading at the, actually, let me do this too. Where's my masking tape? I'm going to retape this because it's falling apart from last class. All right. Yeah, I think it's going to be better right there. All right. Okay, so we're going to measure how far it is up to the bottom. Okay, so up to the bottom of this thing, right now it's reading at 67 centimeters. Okay, so that would probably be pretty consistent throughout the lab, about 67 centimeters. Okay, okay, so that's 0.67 meters. Okay. All right, so Jared, ready to time this?
Yeah.
All right, ready, and go. I'm so sorry, guys. We're gonna have to redo this one. We got a mistrial. The stream was not misgrooved, so I have frictional forces. Yeah, let's try. These first few trials will be the slowest because this is the smallest mass, but they'll be faster as we go on. Okay, right, so ready to restart? Okay, and go. All right, how long was that?
26.55 seconds.
26.55 seconds. Okay, and that was to fall 0.67 meters. Okay, let's do a couple more trials and we'll take an average. Actually, you know what? Okay. Yeah, let's do it. Let's do 2 more trials. Okay, ready? And go. How long is that?
28 seconds.
28 seconds. Okay. And then one more trial for this guy. Okay, ready? And go. Twenty-eight point what?
36.
0.36. Okay. All right. So calculation time. Here, here's six here. Trying to get my calculator in this. Turn the camera a little bit. Okay. So acceleration would be 2x over t squared. So you guys follow along, make sure we're all getting the same numbers. So 2 times 0.67 meters divided by 26.55 squared. This is zero, this is a tiny, tiny acceleration, right? 0.00191. So what you guys getting to? Okay. Then for the next one, I'm getting 0.00171, and then 0.00167. Okay. So those are my acceleration values. Now tension, mg minus a. So the mass was 0.20 kilograms times, let's use 9.8 for gravity. Okay? So 9.8 minus, okay. Now what we're subtracting is an extremely small number. You saw how slowly it was accelerating. So 0.00191. So the tension in this particular stream, it's almost the weight itself, right? It's hardly any different. So 1.96 newtons. That should be true for these other ones too, but let me just check for sure. 171, yeah, 1.96. This guy's also going to be, just confirm that, 167, 1.96, 1.96 newtons. Okay. Okay. Now, remember, if you see any rig like this in an AP question, they'll probably make the mass big enough that this tension would be significantly different enough from the weight that it would matter. Right? But you see in this particular lab, it's almost the same thing. Okay. Angular acceleration, just take each of those, which they're pretty much the same number, 1.96 newtons, divide by the radial size of 0.011 meters. That's going to give me, hold on a minute. Did I do that right? Are you guys getting like 178? Hold on. Something's off. What did I do? Acceleration. Oops. All right. I'm being silly. Oops. Okay. I put in the wrong number. Okay. Acceleration was 0.00191 meters per second squared. If you divide that by 0.011 meters, yeah, this looks right. 0.174 radians per second squared. Looks about right. Point 0171. Looking at 0.155 radians per second squared and 0.152 radians per second squared. Okay. Right, since alpha is one of those values that's going to be on the graph, let's take the average of those. So 174, 155, 152, divided by 3. looking at 0.160 radians per second squared. Okay? Then for the torque, let's do R cross F. So the radius is 0.011, the force is 1.96 newtons. Okay? So that's giving me 0.0 I'll go to a 216, I guess, like 3 sig figs, because it got 3 sig figs everywhere else. Okay. But that number is going to be the same all the way down. Because the force values came out the same number, and we're extremely close to each other. Okay. And the radius, of course, is the same for all those. Right? So there we go. We got one try. Okay. Good so far. Okay. All right, now let's bump this up a little bit. We'll do 300 grams or 0.3 kilograms. We got 100 grammer right here, and it's going to add that to the 200 that's already there. So it'll bring us up to 300. Much like Spartans. Okay. And then, okay, so this thing's still following the 67 centimeters. Right, so radius. Okay. And go.
Nineteen point five five.
19.55 seconds. Okay. All right, try 2. And go.
Eighteen point four four.
18.44. And here's what we'll do is, you guys know, probably pretty good practice, take 3 and take an average. Right? If AP asks you, then say you do 3 trials and take an average, they'll pick you up a point probably somewhere on this exam, right? Let's just do 2, because they're not going to be a whole lot different from each other. So we did 0.67, 0.67. We'll do that all the way down too. Okay, so let's see, 2 times 0.67 divided by 19.55 squared. We're looking at 0.00351. And then see this one, 18.44. This is 0.00394. That to be meters per second squared. Extremely small accelerations. The tension in the string, we've got a mass of 0.3. We got G, we'll call 9.8. Then subtract 0.00351, which is almost nothing. Yeah, so it's 2.94 newtons. This other one should be the same thing, but just confirm that. 394. Yep, 2.94 newtons. The angular acceleration, so I'm going to take that linear acceleration, 0.00351, divide by the radial size of 0.011, and this gives me 0.3. Are you guys getting 0.319? Huh. Interesting. All right, we try this other one. 394. 0.358 radians per second squared. Oh, okay. Actually, that does make sense. Okay. Here's what I'm looking at. See how the mass jumped up about 50% from 0.2 to 0.3? That's an increase of 50%, right? But look what happened to the acceleration values. See how it pretty well doubled? Huh. I wonder why that would be. There actually is a really good reason for that. Does anybody know why? The weight only went up by 50%. The acceleration nearly doubled. Can you guys think why that would be? Hold on to that thought. Might be able to figure it out. Okay. Let's see, R cross F. So 0.011 times 2.94. I might forget to come back to that question, but I'll answer one or another, just maybe indirectly. 323. Right, and then, oh, okay, same thing. 0.0323. 0.0323. And the average of these guys, let's see, 319,358 divided by 2. This is 0.338. Okay. Right, good so far? Okay. Now let's jump this up to 400 grams. Right, 400 grams. There you go. All right, ready? And so it's still falling 67 centimeters, and go.
$15.75.
15.75. All right, so that was 15.75. All right, ready? And go.
$15.89.
15.89. All right, so that was so same falling distance. So 2 times x over t squared is 0.00540. Then the one right below that is 0.00531. So mass times 9.8 minus that number is, let's see, 3.92 newtons. And then, well, this other one's probably going to be the same number. So, yep, 3.92 again. Angular acceleration, so take that linear acceleration of 3.92, divide by the radial size of 0.011. That's given me, okay. Hold on a minute. I made the same mistake twice today. 0.00540 divided by 0.011 is 0.491. Okay. And then the other one is 0.483. So 491, 483. The average of those is 0.487. Okay. And then tau for the torque. I need R 0.011 cross the force 3.92. That's 0.0431. And that's true all the way down. Okay. Okay. Guys all good? Okay. So we got 2 more masses to try. Okay. Let's bump it up to half a kilogram. Here's this guy. Ooh, all right. It's getting pretty heavy now. Okay. It's gonna hold. All right. Oh, sorry, that's not half a kilogram. That's 1 kilogram, isn't it? Oops. Well, I got it on here, so we'll do it while we got it. All right, now this is, yeah, it's still found 67 centimeters. Yeah. Okay. So we're stripping down to 1 kilogram. All right, you guys ready? Okay. And go. Never mind. We're gonna restart that one. Mistrial. Okay. Maybe if I do this now. All right. Okay, good. I think we're gonna get 1 good trial out of this, maybe. So let's cross our fingers for 1 good trial. All right, ready? Okay, and go. Ah, it's going. Ha 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 ha. That would cut my head off. All right, how long was that?
10.11.
10.11. All right, so we're skipping down here to 1 kilogram. We're going to say that was 10.11 seconds. Right? Yeah, let's go back to that because I used to put double the mass on there and that too, which led to many surprises. Okay, let's do the proper half kilogram that I meant to. Then we'll get all our data and we'll crunch it all at once. You know something I don't know, have you guys been noticing this? That right now the string is winding up below this big old massive string, but sometimes it's like winding up here. I don't know why. That confuses me. Huh. Think about that one. And that's gonna keep me awake every night of spring break. Like, wow, why is it winding in different places? Makes no sense. Yeah, there's the question. Why does the string? I don't know. All right, ready? Yeah. And go. I'm gonna be reviewing this tape like the Zapruder film. Oh, did you guys see it jump down at the last second there? That was messed up. All right, so let's call that a mistrial because I think the string was wound around kind of weird. Let's try that again. Yeah, look at that. Look, it's winding up the top now.
probably has to do with the leaning of the.
Yeah, could be, yeah, because it leans over a little bit. Ideally, it wouldn't. Huh. All right, try scan. Ready? And go.
Uh, 13.
13.96. All right, 13.96. Okay. And then we'll do one more. You know what else? All right. I was pretty sure I set this up this morning to not gonna stop be the case, but do you guys see that the string is actually rubbing against these textbooks right here? Right. Well, I hope that doesn't throw stuff off because I was thinking this morning I had the setup where it was actually leaning over the textbooks, but all right. Okay. So that'll add a little bit more friction to the system, but hopefully not a significant amount. But I don't know. All right. So here's the last trial run we're doing today. So for half a kilogram, falling 67 centimeters. Okay, ready? And go. What's that?
14.29.
14.29. Okay. Now, I pulled the string away from the book, so it was just not rubbing up against one like it was before. But it actually took more time to fall down, so maybe that's a point of evidence that maybe the friction wasn't playing a big role. That string rubbing against the books. Okay. So just for 0.67 meters, just make sure that you're getting the same numbers that I am. So to fall 2 times 0.67 divided by 13.96 squared, this would be 0.00688. And this one is, let's see, 14.29, okay, 0.00656. Okay. Let's see, M is 0.5 times 9.8 minus 0.00688 is 4.90 newtons. This number should probably be the same number, just make sure. Yeah, 4.90 newtons. Okay. Angular acceleration, so let's take that 0.0688 and divide by radial size of 0.011. That's, oh, hold on, that doesn't look right. What did I just do? Oh, I'm missing a 0 here. I can insert 0. Okay. Yeah, that looks better. 0.625 radians per second squared. Okay. One right below it. 656 is 0.596. Okay. Now 625 and 596, the average of those is 0.610. Okay. Okay, then torque, R cross F. So R cross F is 0.0539, 0.0539, 0.0539. Okay. And then for the 1 kilogram bag, we'll just do that this one trial because I don't want it to tear my system apart, bust through the floor. And so, see, 2 times 0.67 divided by 10.11 squared. Fast little guy. 0.0131 meters per second squared. Right, then do m times g minus a. That'd be, yeah, ooh, 9.79. Hey, 9.79, that's a shade less than 9.8. That means that accelerating down didn't matter, a tiny, tiny bit. Angular acceleration, so 0.0131 meters per second squared divided by 0.011 meters gives me, 1.191 radians per second squared. The torque value on that was r cross f, that's 0.011 for my r, cross it with my 9.79 newtons, that's 0.108 for the newton meters for the torque. Okay, okay, great. We've got all our raw data now. Okay. You guys good so far? Okay. All right, so now I've got my alpha values, my torque values, right? And here's alpha, here's torque. Right? So I'm gonna switch over to Excel and let Excel make a really pretty graph. Right? While I'm doing that, you guys can probably start scaling that axis and start plotting down points. Okay. So I present screen to share. Okay. I'll bring up an Excel page. Block 2 for you guys. Okay. And then pop in these values. Right, so they went, so this is 0.160, this guy's 0.0216, this guy is 0.338, 0.0323, 0.487, 0.0431, let's see, 0.610, 0.0539, and then the big guy, 1.191 and 0.108. Okay, now let me get you these. Okay, so I did want to show you guys how to create a graph in Excel. Probably most of you guys know, but in case some of you guys need to see it, a lot of times I'll have just Excel like automatically programmed to make it. So let me do this whole thing from scratch. I'm going to get rid of this. Now, what I have done ahead of time is I've taken those cells and I've had them copy paste those numbers down here. So here's all my alpha values. Here's all my torque values. Okay, guys, that? Okay, just in these boxes. Okay. And how do I do that? Well, all I did was just set it equal to that stuff. Set equals the cell for that one, right? Okay, so you just copy pasted it. Okay, is that good there? All right, now how do you create a graph in Excel? Okay. So take a cell where I want to go, say insert. Right? Now, the graph I really like for this class, and different graphs are good for different purposes, but for this graph, for this class, I use the scatter plot over and over again. See the scatter plot? Okay. So then, let's pop this in here. Okay. And hopefully this looks like if you're getting a head start and start making a graph, hopefully what pops up here looks about what you're drawing. So I'm going to right click, go to select data. Does this say select data? Okay. Okay. And then, let's see, add. Okay. And then, oh, look, you got series name, X values, Y values. I don't really care about the name so much, but X values, that's going to be all my alpha values. That's these 5 guys, right? So put those in there. Right? And then my Y values, that's my torque values. That's these 5 guys right here. Put those in. Okay. You know, we was doing this last class, and I don't know why, but let me see what it says. It says the reference is not valid. Okay. So, all right, let's clear that up. I've got a roundabout way to do this stuff. Right. See, what I'll do is I'll just copy paste these numbers right here. So 0.0216, 0.0323, 0.0539, 0.05. Oh, did this come out the same? Hold on. I messed something up, didn't I? What the heck just happened? I'm getting a repeat.
You forgot to do trial 3. You did trial 4 twice.
Yeah. 539. I don't see anything with that.
0.487.
Ah, you know what? Is this even referring to? Here. That's that one. 0.03. That is.
Yeah, you skipped.
Ah, okay. Yeah, thanks. Good catch. So that needs to be this box. This needs to be this box. These other boxes. Okay, so now we're on track, right? Okay. So yeah, thanks. Go back up here, call this guy 0.0431, 0.0539, and 0.108. All right, so let me try this again. So right click, select data, add. Okay, so my X values, I still want these 5, which I'm still happy with, all good. Okay. And my Y values, these, lose them, okay. And, okay, now the same thing happened last class. Let me get rid of this tile. No, like that. Let's go here. See how these first 4 points line up really nice in a straight line, and then that last one, that 1 kilogram guy, is like way the heck off. Right? I don't know why that is. They should all line up in a straight line. Now, of course, there should be a big gap in the graph, but it should be in line with the first 4. Like this last one should be way the heck over here. Oh, look. Oh, I think I see why. This bottom axis is not scaled to. Why did it do that? Hold on, let me pull this back over where I can see it better. Why is that scaled? That doesn't make any sense. It's not supposed to be that kind of graph. Values. Values. Let's see what's messed up here. 102. Here. Okay. And guys, I will keep this going back shortly. Second. I fix some things. All right. I've done like a million of these graphs and I've never run into these set of problems. Right. Okay, let me go back over here. All right. Yes, select data again. Right. But my horizontal axis. Right, messed up. Yeah, this is more like this should okay. Right. See what it is, I just took this column of numbers and just copied it over here. So my X value should be those 5. My Y values should be these 5. Okay. Oh, why is it giving me a different graph? I'll get rid of that first graph. I don't care about those. Yeah, that's what that should look like. All right. Right, so we're all right. All right. So there you go. There's your guys' graph. Okay. So copy down that graph. We'll zoom in a bit. Okay. And while you're at it, I'm going to add a trend line here. Okay. Now, see that they lined up pretty well in a straight line, don't they? Okay. And ideally they should. So that should be a straight line. But it should also be a straight line with an intercept. You guys said that that's also true. So let me do right click, add trend line, equation. So we've got trend line going here. Blow this up. Okay, now question for you guys. what, no, this line actually does have an intercept. It truly does not go through the origin, and it shouldn't, for certain reason. Why, what's a good physical reason that this should not actually go through the intercept? Like, what does the intercept represent? Yeah, the initial friction, right? The friction that it has to overcome just to get moving in the first place. Right? Notice the first weighted tank was like a 200-gram mass guy. Earlier, I tried to start with 100 grams, and that was not quite enough mass to get it going. So I had to up it from it. Yeah, so there is some friction there, and that's what that represents. So this friction represents that at 0 alpha, you do need some initial torque to overcome that initial friction. Okay. And what property of this graph will tell me the answer to this question again? And the question is, what's the rotational inertia? It's the slope, isn't it? The 0.08 number. Right? So there you go. So the answer to this lab is the rotational inertia is 0.0855 kilogram meter squared. Right? So you guys got the graph and you guys got the answer. I equals that slope. All good. Okay. So remember before we started this lab, we tried the textbook value of, well, we looked at the table in the book and said, let's figure out what the I value is using those equations. Okay. And we came up with, here we go, 0.0376. Okay. But remember that was kind of a lower bound, mostly because, well, that vertical pipe added some inertial, some rotational inertia, maybe a few other reasons, but this should be like a lower bound. Right? Oh, and the actual answer came out to like 0.08 something, right? 0.0855, and we were saying that it should be at least this much. Yeah, so that's pretty well consistent with that, isn't it? Right. Okay. Okay, so you guys need to see this one more time. Okay. Everybody got that graph though? You guys done with the graph? Okay, so let me switch over to, well, okay. I'm gonna switch over to projection just for a moment here. Then I'll flip it back there. Okay, so have you guys do a lab write-up here, because one of your FRQs, of course, is going to be experimental design, lab write-up. You have to answer these kinds of questions on the AP exam. Okay, so help you guys out with some of these. Right? We all have the same question, don't we? Which is, what is the rotational inertia of well, that T shape? And you can refer to a diagram. So you can say, what is the rotational inertia? Or you can say, what is the moment of inertia? You could say that too, right? What is the rotational inertia, or what is the moment of inertia of, let's say that system, and you can refer to a diagram. Okay? What measuring tools do we use over the course of this lab? Yeah, there's a meter stick involved, there's a stopwatch. You could argue maybe a balance or a scale, because we were using different masses, right? So it'd be good to have all three of those on here, right? Maybe scalar balance, meter stick, stopwatch. Okay. And then skip these couple sections. The very last question, we all have the same conclusion. The rotational inertia equals, what was it, 0.05 or 855 kilogram meter squared. Right? So there you go. You should have 3 of these 5 sections. Okay. We got 10 minutes left in class. So in the last 10 minutes, I'll give you guys this time to tell me what was the procedure that we used to go about gathering the raw data. And then question number 4, once we had the raw data, what equations did we use to make our way to figure out what the rotational inertia was? Right? And pretty much you guys can just like follow. You can use this table as a checklist left to right. Okay? Pretty, right. So once you finish this, pop this in the grade tray. Most of you guys probably finished by the end of class. If you don't, then just bring it in for spring break. So if you finish it today, then it will be off your hands. So I'm going to stop this recording, but I'm still here. You guys got any questions?